Namaste. In the previous class, we looked at what alkanes are, how they are prepared, what are the different ways in which we can prepare them in the laboratory, and we also got introduced you to the physical properties of alkanes. Post the physical properties, we started with the chemical properties. Under chemical properties, we looked at the first property, which was substitution. Under substitution, we specifically looked at chlorination. And chlorination, we understood with the help of chlorination of methane as an example. And when we did this reaction, we found out that methane undergoes chlorination not to give just one product, but it gives multiple products. And we said we get multiple products like chloromethane, methylene chloride, chloroform, and carbon tetrachloride because of the nature of this reaction. And what was the nature of the reaction? The reaction proceeds via free radical mechanism. So we said any reaction that proceeds via free radical mechanism is composed of three steps. What are the three steps? Initiation, propagation, and termination. And since free radicals are generated during the first step, which are highly unstable, they try to create more free radicals in the subsequent steps such that we get multiple products. And for initiating this reaction, we need diffused sunlight. So this is what we studied in the previous class. That was the first chemical property. In today's class, we will continue further and try to look at the other chemical properties of alkanes. One of the other properties that alkanes show extensively is called as combustion reaction. I'm sure you would have already come across this term called as combustion right from your school. What is meant by combustion? In simple words, combustion is a reaction where you burn something in the presence of oxygen. So this is, in simple terms, what combustion is all about. Now let's look at what happens in the case of alkanes. When alkanes are heated in the presence of air or oxygen, it oxidizes to carbon dioxide and water. So if I take an alkane, we know alkanes are hydrocarbons, which means I have carbon, I have hydrogen. When alkanes are heated in the presence of oxygen, all the carbons which are there in the alkane get converted to carbon dioxide, and all the hydrogens which are there are converted to water. So this is what happens during combustion of alkanes. This reaction is a highly exothermic reaction. Now, what do we mean by an exothermic reaction? An exothermic reaction is a reaction where energy is released during the course of the reaction. The opposite of this reaction is endothermic reaction. Endo means inside, exo means outside, therm means heat. So when I join these two words, exothermic, heat given outside. So these reactions are highly exothermic in nature, giving a lot of energy in the form of heat. Hence, they are used as fuels. So fuels are mainly composed of alkanes because of this property, where they can liberate a lot of energy during the course of the reaction. So let's have a look at the definition again. The reaction in which energy released is called an exothermic reaction. So an exothermic reaction is a reaction where energy is released. Let's take an example to understand combustion. CH4 is methane. When methane reacts with oxygen, we said all the carbons get converted to what? Yes, all the carbons get converted to carbon dioxide and all the hydrogens get converted to water. So this is the general reaction. And during the course of this reaction, we said energy is released. Now, how do we express it? We express it in terms of delta H. Now, you will understand this term better when you understand chemical thermodynamics. Delta H is nothing but change in enthalpy. Delta is a symbol used for change, and H is enthalpy. Now, what is enthalpy? Enthalpy is nothing but heat content present in the system. Change in the heat content is nothing but delta H. You will understand what delta H is, how do you arrive at delta H more specifically when you do chemical thermodynamics. But right now, for our understanding, just understand what is delta H. So delta H has a value, and the value is minus 890 kilojoules per mole. Now you can clearly see that it is negative. Now the moment it is negative, it is understood that it is given out. So wherever you will come across delta H, if delta H is a negative value, then the reaction is exothermic in nature. And what is the amount of energy that is released? 890 kilojoules per mole of methane is what is released when this reaction happens. Clear? So this is an example for that. If I need to write a general equation for combustion for any alkane, now we looked at methane. If I take any alkane, we know the general formula is CnH2n plus 2. This will react with 3n plus 1 by 2 moles of oxygen. If I take any general alkane having the general formula CnH2n plus 2, it will react with 3n plus 1 divided by 2 moles of oxygen to give n moles of carbon dioxide and n plus 1 moles of water. This is a very, very, very important relationship. Now, with this relationship or with this understanding, you can actually go and write the combustion equation for any alkane, whatever be the alkane. You will know what is the amount of oxygen that is required. So let me repeat. CnH2n plus 2, for that alkane, I need 3n plus 1 divided by 2 moles of oxygen, which will give us n moles of carbon dioxide and n plus 1 moles of water. If n is 4, for example, then it is C4H10, which is butane. For C4H10, which is butane, and n is equal to 4, what is the number of moles of oxygen required? All what you need to do is put the n value in that relationship there, 3n plus 1. So if I put that relation n value there, 3 into n, n is nothing but 4. So 3 into 4, 4 3s are 12, plus 1, 13 divided by 2. So 13 by 2 moles of oxygen is what I require in order to produce n moles of CO2. What is n here? 4. So 4 moles of CO2 and n plus 1 moles of water. N is 4. So therefore 4 plus 1 is nothing but 5 moles of water. So I hope you have understood the use of this relationship. Very, very important relationship. There's one more combustion called as incomplete combustion. Now, what combustion we saw just now is complete combustion, because all the carbons are getting converted to carbon dioxide and all the hydrogens are getting converted to water. That is complete combustion. Then what is meant by incomplete combustion? I'll take the same example as before, CH4. If I take CH4 and react it with oxygen, look at the product that I'm getting here. Carbon plus 2 moles of water. So I'm getting carbon plus 2 moles of water. Now you can clearly see the difference between this equation and the previous equation. Now when we looked at complete combustion, what were the products? Carbon got converted to, yes, carbon got converted to carbon dioxide. Whereas in this case, carbon from methane is isolated as elemental carbon. This is incomplete combustion. So when incomplete combustion of methane happens, carbon black is formed. So we call this elemental carbon as carbon black. And where is this used? This is used in inks, black pigments, and filters. So it's a very, very important reaction commercially. where the product is used in a lot of things that we use on a day-to-day basis. So I think now it's very clear what's the difference between complete combustion and incomplete combustion. And you will see one more thing. The moles of oxygen that are used, if it is complete combustion, you have more number of moles of oxygen that is used, whereas in the case of incomplete combustion, we actually carry this reaction out at low moles of oxygen. So here for CH4, only 1 mole of oxygen is used up, whereas in the previous case, you would remember that we had used 2 moles of oxygen. The next chemical reaction is called as controlled oxidation. Controlled oxidation. Now, once again, the name itself will give you an idea about what's happening during the reaction. Now, oxidation, pretty straightforward, is reaction with oxygen or addition of oxygen. Reaction is controlled. Controlled means from outside, there are certain factors or there are certain parameters that will decide the course of the reaction. Hence, the oxidation is called as controlled oxidation. Alkanes on heating with limited supply of oxygen or air at high pressure and in the presence of a catalyst give different products. So when you clearly see the statement here, which talks about controlled oxidation, you can see what are the factors that are controlling this oxidation. One, there is limited supply of oxygen. Two, high pressure. And three, presence of a catalyst. So pressure, catalyst, and limited supply of oxygen is what is used to control the products of oxidation. Let's take an example here. Methane is what again I take, is made to react with oxygen in the presence of copper at 523 Kelvin and 100 atmospheric pressure. So you can clearly see temperature is also involved, which is quite high. A catalyst is also involved, and pressure is also involved. So all the three external factors which will alter the course of the reaction is present: catalyst, temperature, pressure. And on top of that, oxidation is not complete. Oxidation is carried out with limited supply of oxygen. So when we do this, the product obtained is methanol. The product obtained is methanol. So methanol is what is obtained when methane is reacted with oxygen in the presence of copper, 523 Kelvin and 100 atmospheres. Now you can clearly see the difference between the three cases that we have seen so far. First one was complete combustion, where the products were carbon dioxide and water. Second one was incomplete combustion, where the product was carbon black and water. And in the third case, controlled oxidation, where the product is methanol. Let's take one more example. If I take the same compound methane and react it with molybdenum oxide and heat, now you can see the difference here. There's a change in the catalyst that is used. In the previous case, we used copper. Here we are using molybdenum oxide. If you use molybdenum oxide, look at the product that's obtained. The product that's obtained is methanol, which is formaldehyde. When we used copper, the product was methanol, an alcohol. Whereas when I use molybdenum oxide, the product is an aldehyde, which is methanol, also called as formaldehyde. And water, of course. This is ethane. CH3 is nothing but C2H6, which is ethane. Ethane, when it reacts with oxygen in the presence of manganese acetate as a catalyst and you heat it, we get acetic acid. We get acetic acid and water as the product. So you can clearly see that the nature of the catalyst or the type of the catalyst is really going to determine the type, the kind of product that is obtained. If you use copper, you get an alcohol. If you use molybdenum oxide, you're getting an aldehyde. If you're using manganese acetate, you're getting an acid. So the catalyst will decide what is the final product during the course of controlled oxidation. Let's take one more example here. This is an example of a tertiary alkane. What's a tertiary alkane? I have a tertiary carbon. Now we have already seen what a tertiary carbon is. A tertiary carbon is a carbon which is in turn attached to three other carbon atoms. The name of this compound is 2-methyl propane. And I have a tertiary hydrogen. Who is a tertiary hydrogen? A hydrogen that is attached to a tertiary carbon is called as a tertiary hydrogen. Now, when this compound is made to undergo controlled oxidation in the presence of KMnO4, liberating nascent oxygen, look at the product. The product is an alcohol, tertiary alcohol. In place of H, what's the change that's happened during the course of the reaction? In place of H, I have OH. Or in other words, oxygen has got incorporated between the tertiary carbon and the tertiary hydrogen, giving us an alcohol, which is a tertiary alcohol, which is called 2-methyl propan-2-ol. By now, you should be quite familiar with the nomenclature, IUPAC nomenclature of alkanes and some compounds like alcohols, aldehydes, ketones, etc. So 2-methyl propan-2-ol is the IUPAC name. This is methyl cyclohexane. Please remember, this is not benzene. Some of us tend to write benzene without the double bonds inside. Now, that's completely wrong because that is not benzene. That will be cyclohexane. So this is cyclohexane. To cyclohexane, I have a CH3 group that's attached. Hence, this is called as methyl cyclohexane. When methyl cyclohexane undergoes the same reaction, what do you think is the product? I want you to complete this product now. I hope you have kept a book with you right now to make a note. So I want you to complete this reaction. Find out what is the product obtained. Methyl cyclohexane upon controlled oxidation with KMnO4 will give us what? Reaction is quite similar to the previous example. Done? All right. The product obtained is this 1-methyl cyclohexanol. Now, to the first carbon where you had CH3, you also have a hydrogen. Because this is cyclohexane, each carbon will have two bonds, two hydrogens to be more specific. The first carbon has a CH3 and a hydrogen. If I have to just use one of the annotation tools to help you. So this is hydrogen. Okay. So what's happened during the course of this reaction? Oxygen has got incorporated between carbon and hydrogen. And hence, instead of H, what do I have in the product? I have OH. This is just like what's happened in the previous case. In the previous case, oxygen gets incorporated between carbon and hydrogen to give you OH. Same way, the nascent oxygen gets incorporated between carbon and hydrogen to give you OH, yeah, which is 1-methyl cyclohexanol. Clear? All right. So let me just undo this. Let's look at the next reaction. We looked at oxidation. Okay, so before the next reaction, let's solve a few MCQs. I've just incorporated few MCQs at the end of a few significant reactions so that you will know what are the kinds of questions that can be asked in the competitive exams. These are simple MCQs, by the way, not complicated ones, just to give you an idea that we can also create MCQs from PU concepts. So the first one, on controlled oxidation of ethane in the presence of manganese acetate, what do we get? Option A, methanol. Option B, acetic acid. Option C, methanol. Or option D, carbon black. On controlled oxidation of ethane in the presence of manganese acetate, what do we get? We get acetic acid. Pretty straightforward if you would have understood that reaction. Let's look at one more. Number of moles of oxygen required to complete combustion of C4H10. So there's a mistake in the question. It is not combination, it is combustion of C4H10. I think we saw the same example there, so it should be pretty straightforward. Is it option A, 13? Is it 13 by 2, 7, or 8? Remember, this is where the general equation becomes very important. It comes into force to help you. We saw that equation, right? So if you follow that equation, for n is equal to 4, we need, yes, 13 by 2 moles of oxygen. The next chemical reaction is isomerization reaction. Now we have already come across this term called as isomerization. Who is an isomer? An isomer is a compound, or isomers are compounds where they have the same molecular formula but they differ in their structure. These are called as isomers. You also saw the different types of isomerism: structural isomerism, stereoisomerism. Under structural, you saw subsequent types: chain, position, link, etc. Let's look at what happens in isomerization reaction. As the name itself indicates, this would be a reaction which will produce isomers of alkanes. Now, how do we get isomers starting from alkanes? Now, when alkanes are heated with anhydrous aluminum chloride and HCl. So what is required? Anhydrous aluminum chloride and HCl. When alkanes are heated with anhydrous aluminum chloride and HCl, we get the corresponding isomers. For example, if I take N-hexane, when it is made to react with anhydrous aluminum chloride and HCl, we get the isomers of N-hexane, which is 2-methylpentane and 3-methylpentane. Now, when you look at the starting compound and the final products, all of them have the same molecular formula, but what are they differing in? They're differing in their structure. And specifically, how are the two products differing? Based on the position of CH3. So whether the CH3 is in the second position or whether it's in the third position is what is different. But all of them have the same molecular formula. Such compounds are isomers, and a reaction which gives isomers is called as isomerization reaction. There's one more reaction called as aromatization reaction. Now, where is this obtained from? If you observe the name of the reaction, aromatization, it is probably derived from aromatic compounds. So, isomerization is a reaction where isomers are produced. Aromatization reactions are reactions where aromatic compounds are produced. So, aromatic compounds are produced during the course of this reaction. Now, how do we get aromatic compounds? When alkanes having 6 or more carbon atoms on heating to 773 Kelvin at 10 to 20 atmospheric pressures in the presence of catalysts like V2O5 or Cr2O3 or MO2O3 over alumina, they produce benzene or its homologues. So this is the definition, or this is what happens when you take an alkane and convert it into a aromatic compound. Now, one thing is pretty straightforward here. It says it should have 6 or more carbon atoms. Natural, isn't it? Because benzene has 6 carbons, and I need to have a minimum of 6 carbons in order to produce benzene. So I cannot have alkanes having 3 carbons, 2 carbons, producing benzene using this reaction. I need alkanes which have a minimum of 6 carbons to get our aromatic compound. And the reaction does not happen under normal conditions. Reactions require very high temperature, requires very high pressure, and the presence of a catalyst. So only when you do that, we can produce benzene or its homologues. Homologues are nothing but derivatives of benzene, where you have substituents attached to the benzene ring. So this reaction is what is called as aromatization reaction. So this is N-hexane. When N-hexane reacts with our catalysts, chromium oxide or vanadium oxide or molybdenum oxide at 773 Kelvin. Now you can see we have written hexane in a different way. The reason is just so that you can relate to the final product. And you can clearly see how the final product would be. The final product is nothing but benzene. Benzene is C6 at 6. And one more thing that you would have understood by looking at the reaction, the number of carbons remain the same from the starting compound to the final product, but the number of hydrogens are different. The number of hydrogens are different because in the case of N-hexane, we have 14 hydrogens, whereas when you look at benzene, there are 6 hydrogens. So 14 minus 6, 8 hydrogens are removed from this alkane in order to get benzene. Let's solve a few MCQs. When N-heptane is subjected to aromatization, the product is what? When N-heptane is subjected to aromatization, what is the product? Now we saw N-hexane in the example. Now you need to find out what will N-heptane give if it is made to undergo aromatization. So before I give you the options here, I want you to do this. I want you to solve this, write N-heptane, and then carry out aromatization. So let me show this reaction for you so that you can refer. This is N-hexane. If I take N-heptane, heptane means C7, so there will be one more carbon. That's extra. What do you get? Let me give you a hint. Hint is the 6 carbons of heptane will form the benzene ring, just like N-hexane. 7th carbon will be a substituent. Seventh carbon will be a substituent. Clear? So I've already given you the hint and the final product. All I want you to do is write the reaction. All right. So if we have written the reaction, let's have a look at the options. Option A, benzene. Option B, toluene. Option C, methyl benzene. And option D, both B and C. Now, one thing is pretty straightforward. We cannot get benzene alone because I'm not starting with N-hexane. If I was starting with N-hexane, I would have got benzene. But I'm starting with N-heptane. And I told you one carbon is extra and that carbon will become a substituent. And that substituent will be the methyl substituent that will be attached to benzene. So option C, methyl benzene, can be one of the answers. Why am I saying it can be one of the answers? Because methyl benzene has a common name. And what is a common name? Yes, the common name of methyl benzene is toluene. So toluene is the common name. So therefore, when you look at this question here, option B says toluene, option C says methyl benzene. So your answer will be both B and C. Got that? Second one, 2-methyl pentane and 3-methyl pentane are what? Now, where did you come across 2-methyl pentane, 3-methyl pentane? Yes, you came across this in isomerization reaction. So 2-methyl pentane and 3-methyl pentane are they chain isomers? Are they position isomers? Are they both chain and position isomers? Or are they metamers? What are these? You already came across the different types of isomerism: chain, position, functional. What is this? The difference between 2-methyl pentane and 3-methyl pentane is where is the methyl group attached. In the first case, the methyl is attached to the second position, and in the second case, methyl is attached to the third position. Since these two vary based on the position of the methyl groups, these two isomers are called position isomers. Reaction with steam. This is one more significant reaction. Steam is nothing but water in the vapor form. So what happens? Methane reacts with steam at 1273 Kelvin in the presence of nickel catalyst, giving carbon monoxide and hydrogen. So it gives carbon monoxide as the product, and along with that, we have hydrogen as the byproduct. This method is actually used to prepare hydrogen gas in the industries. So this is a very, very important commercial reaction because it is used in the manufacture of hydrogen, where hydrogen is used for a lot of industries. So let's have a look at the chemical reaction. CH4 plus water in the form of steam gives us carbon monoxide, of course, in the presence of nickel and heat, carbon monoxide, and hydrogen. Hydrogen is produced in large quantities, hence, this is used to prepare hydrogen gas in the industry. The next reaction is called as pyrolysis or cracking. Now let's understand this word. I think you would have already come across pyrolysis or cracking sometime in your school, where you studied petroleum products. You would have come across that. You might have forgotten it by now. So let's try to understand what is pyrolysis. Now, the word pyrolysis can be broken into two parts. The word pyrolysis can be broken into two parts: pyr and lysis. Lysis means break. Lysis means what? Break. Pyr means heat. Pyr means energy. So breaking something in the presence of heat is what is called as pyrolysis or cracking. Higher alkanes on heating to high temperatures. So pyre is high temperature. On heating to high temperature, decompose into lower alkanes, alkenes, etc. Higher alkanes means alkanes containing more number of hydrogens. When I take that and heat it under high temperature, they break down, decompose, or lyse to give lower alkanes, alkenes, etc. This reaction is called as pyrolysis or cracking. The decomposition of higher alkanes to smaller fragments is called as pyrolysis. So this is the definition of pyrolysis. The decomposition of higher alkanes to smaller fragments or smaller alkanes or alkenes is called as pyrolysis. This reaction takes place through the free radical mechanism. Now, we've already come across free radical mechanism. Which are the three steps in the free radical mechanism? Yes, initiation, propagation, and termination. Proceeds via free radicals. Hence, you just do not get one product, you get multiple products. Let's take an example. C6H14, nothing but hexane. If I take hexane and heat it at 773 Kelvin, these are the different combinations of products that I get upon pyrolysis. One combination is C6H12 plus H2. Another combination C4H8 plus C2H6. And the next combination C3H6 plus C2H4 plus CH4. So you can clearly see that one compound is not giving me one final product. It is giving me multiple products. And why am I getting all these multiple products? It's because of free radical mechanism. And you can see that you get lower alkanes also, alkenes also during the course of pyrolysis. If I take C12H26, it is called as dodecane, and carry out pyrolysis in the presence of platinum, palladium, or nickel at 973 Kelvin, look at the products obtained. C7H16, C5H10, which is heptane, pentene, and other products. Pyrolysis is used to prepare petrol or kerosene from gasoline. So pyrolysis is used to prepare petrol or kerosene from gasoline. Now this is what you would have studied in your school. Gasoline is obtained from crude oil. From crude oil, when you do fractional distillation, you get various components. And from gasoline, if you carry out cracking or pyrolysis, you get petrol or kerosene. So pyrolysis is again one more very, very important commercial reaction. Let's have a look at few MCQs. Ethane under nitration gives us what? Will it give a nitro compound? Will it give an amine? Will it give a nitro compound of methyl or methyl amine? Will it give nitroethane, or will it give an amine? Will it give nitromethane, or will it give aminomethane? Nitration is a reaction where a nitro group is introduced during the course of the reaction. So therefore, ethane upon nitration will give us ethyl nitrate, C2H5NO2. Propane under combustion gives. Pretty straightforward, right? Propane upon combustion will give us what? Methane and water, oxygen, water and heat, carbon dioxide, water and heat, none of the above. Propane under combustion. Now, this was the first reaction that we studied today. We said combustion reactions are highly exothermic, which means they liberate a lot of energy in the form of heat. And combustion, if it is complete, will give carbon dioxide and water. So until unless they do not specify anything, you will assume that it is complete combustion. If they would have mentioned incomplete combustion in the question, then probably you would have looked at a different way to arrive at the answer. But here it says under combustion. If they just mention combustion, it assumes that it is complete combustion. So complete combustion of alkanes give us what? Yes, carbon dioxide, water, and heat. Halogenation is a carbocation reaction, carbanion reaction, free radical reaction, or an alkyl halide reaction. Halogenation was the first chemical property that we studied in the previous class. It's a free radical reaction. So pretty straightforward question out there. Pyrolysis involves dehydrogenation, cracking, both, or none of the above. Does pyrolysis involve removal of hydrogen, or does it just involve breakage or decomposition, which is also called as cracking? It just involves cracking, is it? No. Oh, the answer has already come up there. It involves both. Dehydrogenation, there is removal of hydrogen also. At the same time, there is breakage. So both dehydrogenation and cracking happens during pyrolysis. Whereas when you looked at aromatization, in aromatization, remember when we started with N-hexane, we got benzene. There was removal of hydrogen. Removal of hydrogen is called dehydrogenation. So there was only dehydrogenation there. Whereas in pyrolysis, it involves both dehydrogenation as well as cracking. Ethane under dehydrogenation. Hey, we just spoke about dehydrogenation and we have a question here. Ethane under dehydrogenation gives ethene, propene, methane, or none of the above. Now you can clearly eliminate option B, because when I'm starting with ethane, there are only 2 carbons. I cannot get propene, which has 3 carbons. So I can eliminate B. I will also eliminate C because dehydrogenation does not involve breakage. Dehydrogenation is just removal of hydrogen. So when I remove hydrogen from ethane, I will get ethene as the product. All right, so that's it for today's class. I want you to make a note of the homework for today. Take down the first homework. I want you to write the chemical reaction for aromatization of N-heptane. Write the chemical reaction for aromatization of N-hexane. That's the first one. Second, I want you to write the reaction for pyrolysis of N-hexane. Reaction for pyrolysis of N-hexane. That's the second homework for today. Take down one more homework, the third one. Starting from methane, carry out combustion, incomplete combustion, and controlled oxidation. Starting from methane, carry out combustion, incomplete combustion, and controlled oxidation. So the starting compound is the same, which is methane, but when you carry out each of the three, you get multiple different products. All right, so these are the three homeworks for you today. Make sure you go through the presentation and then get your doubts clarified and then solve the homework. So this is for today's class. In the next class, we will start with the next set of compounds called as alkenes. So until then, namaste. Thank you.